In this video, we shall learn to figure out significant figures given a measurement. And there are no rules to memorize, I promise. Say these are the measurements obtained for the mass of a pencil when measured by using two different scales. In the first measurement, its mass is measured up to 1 decimal place. In the second measurement, its mass is measured up to 2 decimal places. Remember, this trailing 0 in the decimal part came out of the measurement process. I did not add it. We made an effort to know the value of this digit, and it happened to be a 0. It could have been any other number instead of a 0. And in this measurement, the implied uncertainty is plus or minus 0.1 grams. And in this measurement, it is plus or minus 0.01 grams. Obviously, the amount of uncertainty is less in this measurement than in this measurement. So, this measurement is more precise than this measurement. So, by looking at these two measurements, we understand that if there are more digits in the measurement, it is more precise. Then the obvious question is, if more digits mean more precision, does every digit present in the measurement contribute to the precision of the measurement? Let us see. Let us take this measurement, that is 16.1 grams. And you know, I can multiply this with 1,000 and divide it with 1,000 without changing its value. Now my question is, by doing this, did we change the precision of the measurement? Think for yourself. In my opinion, no. The precision of this and the precision of this measurement are one and the same. By multiplying and dividing it with the same number, the precision would not change. Now let us absorb this 1,000 into the unit. You know 1,000 grams is 1 kilogram. So we can write this as 16.1 over 1,000 kilograms. And you know, during division, for each 0 in the denominator, we have to move the decimal point by 1 position to the left. So, for 3 zeros, we have to move the decimal point by 3 places to the left, and this will be the new position of the decimal point, and there is an empty space between this decimal point and this 1. So, we can write it as dot space 161 kilograms. Now what should we put here? By convention, we have to fill this space with a 0 to clearly indicate that there is an empty space between this decimal point and this number. This is by convention. So finally, the measurement we have is 0.0161 kilograms. So all I did here is expressed this measurement in kilograms. Now if you look at this measurement, you will find more digits than there are here. Now the question is, do you think this is more precise than this? No. So though this value has an extra 0 in addition to the 3 digits that are present in the original measurement, it has the same precision as the original measurement. When we chose to convert this measurement from grams to kilograms, we had to introduce this 0 to place the decimal point in the correct location. Otherwise, this 0 has no significance or no purpose. Therefore, this 0 does not contribute to the precision of the measurement. So to answer our question, not every digit present in the measurement contributes to the precision of the measurement. Now let us consider that original measurement of 16.1 grams again. We can write it as 16.1 multiplied by 1 gram. These two are one and the same. And you know, in 1 gram there are 1000 milligrams. So I can replace 1 gram with 1000 milligrams. So it becomes 16.1 multiplied by 1000 milligrams. Now let us absorb this 1000 into the value of the measurement. During multiplication, for each 0, we have to move the decimal point by 1 place to the right. So for 3 zeros, we have to move it to the right by 3 places. So this will be the new position of the decimal point. So we can write it as 161 space dot milligrams. Now again we have to fill these empty spaces with zeros. So the value of this measurement in milligrams becomes 16100 dot milligrams. Again, in this value there are more digits than there are in the original measurement. Does it mean that this is more precise than this? No. These two zeros are introduced in this value so that we can place the decimal point in the right location, as in this case. So these zeros are placeholder zeros. They do not serve any other purpose. Therefore, these two zeros do not increase the precision of this measurement either. And the digits that contribute to the precision of the measurement are the useful or the meaningful digits. And these meaningful digits are what we call the significant figures. So in this measurement, there are 3 significant figures. And in this measurement also we have 3 significant figures because these two zeros are not meaningful. They are just placeholder zeros. Again, in this measurement also, there are only 3 significant figures because this 0 is not meaningful as it is a placeholder 0. And here is what we learned so far. We started with the original measurement of 16.1 grams for the mass of the pencil. And when we converted it into kilograms, we obtained a value of 0.0161. And when we converted it into milligrams, we obtained a value of 16100 dot milligrams. Now, though these values have different number of digits, they all have the same number of significant figures. That is, these 3 have the same precision. Each of these values has 3 significant figures. So, converting a measurement from one unit to another unit does not change its precision or the significant figures. And here is another very important observation that we should make. To convert this measurement from grams to kilograms, we moved the decimal point by 3 places to the left. And to convert it into milligrams, we moved it by 3 places to the right. So, the location of the decimal point is not the same in these 3 values, obviously. Here it is between this 6 and 1, and here it has moved by 3 places to the left of the original place, here 3 places to the right of the original place. But still, these 3 have the same precision and the same number of significant figures. That means the location of the decimal point has no bearing or no effect on the precision of the measurement or the number of significant figures. So converting the measurement from one unit to another does not change the precision or the number of significant figures. And the location of the decimal point in the number has no effect whatsoever on the precision of the measurement or the number of significant figures. And if that is the case, can we ignore the decimal point altogether for the purpose of figuring out the number of significant figures? I think we can. And with that, we are ready to figure out the number of significant figures. See, measurement is a number. And if the number contains a decimal point somewhere in it, it is called a decimal. And if it does not contain a decimal point, it is an integer. And some integers end with one or more trailing zeros like these, and some integers end with a non-zero digit. They do not contain trailing zeros like these. So every measurement must fall into one of these three categories. Let us start with decimals. How many significant figures are there in this measurement? As we just discussed, the location of the decimal point has no effect on the number of significant figures. So we can ignore this decimal point altogether for the purpose of figuring out significant figures. So rewrite this number without the decimal point. That will be 18345. Then to get the number of significant figures, drop every digit that does not change its magnitude and count the remaining digits. As simple as that. Now, I cannot drop any of these 5 digits because dropping any of these digits will change its magnitude. So I have to keep all these 5 digits. So the number of significant figures in this case is 5. How many significant figures are there in this example? Again, rewrite this number without the decimal point. It will be 0009067. Then drop every digit that does not change its magnitude. See, these leading zeros does not add to the magnitude of this number. So we can strike off these 3 zeros. But we cannot remove any of the remaining 4 digits without changing its magnitude. So we have to count all these 4. So the number of significant figures here is 4. In this example, again, drop this decimal point and rewrite that number. It will be 0089. Again, these 2 leading zeros do not contribute to its magnitude, but these 2 contribute to its magnitude. So the number of significant figures here is 2. And in this case, if you drop this decimal point, it becomes 124090. And every digit is needed to maintain its magnitude. If you drop any of these digits, even this trailing zero, its magnitude would change. So you have to count all of them. So the number of significant figures here is 6. And in this case, if you drop this decimal point, it becomes 006098030001. Again, these 2 leading zeros are useless and every other digit contributes to its magnitude. So count every other digit. Is it 9? So there are 9 significant figures in this measurement. And in this measurement, there are 4 significant figures and in the 7th measurement there are 5 significant figures. So figuring out significant figures in case of decimals is very easy. Just ignore the decimal point, strike off all the digits that do not change its magnitude and count the remaining digits. You don't have to memorize any rules to do this, right? So we had no problems at all in figuring out the number of significant figures in case of decimals. So decimals are sweet. Then what about integers with no trailing zeros? Integers like these, they are even sweeter. How do we know the number of significant figures in this measurement? Same as before. And moreover, we don't even have a decimal point to ignore. So drop every digit that does not change its magnitude. In this measurement, you cannot drop any of these digits. Dropping any of these digits would change its magnitude, so count them all. So the number of significant figures is 3. And in this example, this leading zero can be dropped because it does not contribute to the magnitude of the measurement. So count the remaining 2 digits that contribute to its magnitude. So the number of significant figures here is 2. And in this example, you can ignore all these leading zeros, and this is the only digit that contributes to its magnitude. So the number of significant figures is 1. And here, every digit present in this measurement contributes to its magnitude, so count them all. How many are there? 4 plus 4, 8 plus 4, 12. So the number of significant figures here is 12. And again, in this example, every digit contributes to its magnitude, so the number of significant figures is 6. So a cakewalk, right? And here comes the troublemaker. Integers with 1 or more trailing zeros are a problem. Why? Let us see. Let us say we measured the mass of that pencil using 3 different scales with different precisions. And here are the measurements we obtained. And you know how to figure out the number of significant figures in case of decimals, and I don't want to repeat myself. In this measurement, there are 3 significant figures. Here there are 4, and there are 5 significant figures in this measurement. Now for some reason, we wanted to convert them into milligrams. For that, you have to multiply each of these measurements with 1000. And during multiplication, for each zero, you have to move the decimal point by 1 place to the right. So for 3 zeros, we have to move the decimal point by 3 places to the right. So the first measurement becomes 16100 dot milligrams. The second measurement becomes 16100 dot milligrams. And the third measurement also becomes 16100 dot milligrams. Now, if you are given these 3 values and you do not have access to these original measurements, what do you think about the number of significant figures or the precision of these 3 measurements? Now, by looking at these 3 values, you might think that they have the same precision and the same number of significant figures because they are identical. But when you look at the original measurements, you would understand that they are not identical. They have different precisions and different number of significant figures. So it is impossible to tell that these 3 measurements have 3 different precisions just by looking at these values. Now, why did we run into this confusion or this situation? That is because of these trailing zeros. See, in this case, these two trailing zeros came out of the measurement process. I did not add them for this conversion. Whereas in this case, one of the zeros came out of the measurement process and I added 1 0 during this conversion process so that I can place the decimal point in the right location. So out of these two zeros, 1 0 came out of the measurement process and 1 0 is a placeholder 0. Whereas in this case, both these zeros are added during this conversion process so that we can place the decimal point in the right location. And you know, trailing zeros in the decimal part of a number are significant. They contribute to the precision of the measurement. I explained that before. So in this measurement, these two zeros are significant because they came out of the measurement process. In this case, one of the zeros is significant and the other one is not. And in this case, neither of these trailing zeros are significant. But by looking at these measurements, it is impossible to differentiate these zeros. Then how do we convey the reader that in this case, both the zeros are significant? In this case, one is significant and one is not. And in this case, neither of them are significant. You have to find a convention. And the convention that most books follow is, if the trailing zeros are significant, then leave this decimal point there. And if none of the trailing zeros are significant, then drop the decimal point. So if the measurement given is 16100 milligrams without the decimal point, understand that these two trailing zeros are not significant. So in this measurement, there are only 3 significant figures. And if the measurement given is 16100 dot milligrams, then understand that all the trailing zeros are significant. So here there are 5 significant figures. Then what about this case? This convention does not cover this case. That is why some textbooks follow a slightly different convention. That is, they put a dot or a bar on the last significant digit of the measurement. So in this case, they will write it as 16100 with a dot or bar on this one. So this means this is the last significant digit in this measurement, and any digit after that is not significant. So here there are 3 significant figures, and in this case we can write it as 1610 bar 0 milligrams. And because this is the last significant digit, anything after that is not significant. So there are 4 significant digits here, and this measurement can be written as 16100 with a bar on this last 0. So there are 5 significant figures in this measurement. So in case of integers with 1 or more trailing zeros, we need to depend on such kind of conventions to figure out the number of significant figures correctly, and that is a big annoyance. And in the next video, I will explain how to write measurements more elegantly to convey the number of significant figures without any confusion and without needing any convention. But before we end this video, let us work out a few examples quickly. Here we have an integer with trailing zeros, and there is no decimal point at the end. So these trailing zeros are not significant by convention. So there is only one significant figure in this measurement. Here we have a decimal, and in case of decimals you can ignore the decimal point and write it as 100 and remove any digit that does not contribute to its magnitude. Here all these three digits contribute to its magnitude, so the number of significant figures here is 3. Here there is only one digit, so the number of significant figures is 1. This can be written as 0, 4, 5, 6 after ignoring this decimal point, and we can strike off this 0 because it doesn't contribute to its magnitude, whereas these three do. So the number of significant figures is 3. This can be written as 0, 0, 0, 0, 9, 8, 2. These four do not contribute to its magnitude, so the number of significant figures is 3. This can be written as 9800 after ignoring this decimal point, and all these four digits contribute to its magnitude, so the number of significant figures is 4. This can be written as 302010 after ignoring this decimal point, and we need all the 6 digits to maintain its magnitude, and this can be written as 40004 after ignoring this decimal point, and all the 5 digits are significant because they all contribute to its magnitude. Again we have an integer with a trailing 0 but without a decimal point in the end. So by convention this trailing 0 is not significant. So here we have only 2 significant figures. Here all the 3 digits are required to maintain its magnitude. So the number of significant figures is 3. And in this case, again we have an integer with a trailing 0 but without a decimal point in the end. So first drop all the digits that do not contribute to its magnitude. And this trailing 0 is also not significant because there is no decimal point in the end by convention. So there are 3 significant figures here, and in this case we have a decimal, so drop the decimal and write it as 000567, and these zeros are not significant, so there are only 3 significant figures here, and this can be written as 10 after ignoring this decimal place, and we need both the digits for its magnitude, so the number of significant figures here is 2. Then we have this question. By definition, the boiling point of water is 100 degrees centigrade. How many significant figures are there in it? See, this is by definition. And by definition, the boiling point of water is exactly 100 degrees centigrade. That is 100 with an infinite number of zeros in the decimal part. And every digit contributes to its precision. So all these digits are significant figures. So there are an infinite number of significant figures in this value. Then this question says there are 12 eggs in an egg carton. How many significant figures are there in it? Eggs are counted, they are not measured, and any value obtained by counting is an exact value. So we can write it as 12 with an infinite number of zeros in the decimal part, and every digit is a significant figure. So there are again an infinite number of significant figures in this value. Then this says the mass of an orange is 214.59 grams. How many significant figures are there in its mass expressed in milligrams? Remember, the number of significant figures do not change when it is converted from one unit to another unit. So simply figure out the number of significant figures in the given measurement. And here there are 5 significant figures. So the answer to this question is 5.